And this is the part most people never hear. Because while the slow heating of the sun is inevitable, predictable, almost polite in cosmic terms, the sun is also volatile, violent, and occasionally reckless. Our star isn't a calm, glowing lamp in the sky. It's a churning sphere of plasma held together by gravity and rage. Its surface boils at thousands of degrees. Magnetic fields twist, snap, and reconnect with explosive force. And when that tension releases, it doesn't do so gently. It lashes out. These outbursts are called solar flares and coronal mass ejections. Massive eruptions that hurl billions of tons of charged particles into space at millions of kilometers per hour. And Earth is not always lucky enough to dodge them. When one of these solar storms is aimed directly at us, it slams into our planet's magnetic field like a cosmic sledgehammer. Most of the time, that magnetic field protects us. It bends the particles, lights up the sky with auroras, and we carry on with our day. But protection is not immunity. We know this because it has already happened. In 1859, a solar storm known as the Carrington event struck Earth. Telegraph systems caught fire. Operators were electrocuted. Sparks jumped from equipment. And this was in a world with no power grids, no satellites, no global internet. If that same storm hit today, the damage wouldn't be measured in inconvenience. It will be measured in decades. Modern simulations suggest a Carrington-level event could knock out power across entire continents. Transformers would melt. Satellites would fail. GPS would vanish. Financial systems would freeze. Hospitals would lose critical infrastructure. Food supply chains would collapse within weeks. And here's the unsettling part. Events like this aren't rare on stellar timescales. They're inevitable. The sun produces superstorms. The only uncertainty is timing. Now zoom out. As the sun continues to age and grow more energetic, these outbursts become more intense. The solar wind strengthens. Radiation levels rise. Earth's atmosphere, the thin layer of gas keeping us alive, slowly erodes under the constant assault. Mars didn't lose its atmosphere overnight. It lost it piece by piece, molecule by molecule, and the same physics applies to us. Even before the oceans boil, even before plants disappear, Earth becomes harsher, more radioactive, more unstable, less forgiving, which brings us to the uncomfortable truth. Human civilization depends on stability, predictable seasons, reliable technology, a narrow temperature range, a calm star, and we are orbiting a star that will not stay calm forever. This means our long-term survival was never about stopping the sun. That was never an option. Stars don't negotiate. They don't care about intelligence or culture or history. They evolve. The only real question humanity faces is this: will we learn to move before the sun forces us to? Because one day, whether by slow heating or sudden fury, the sun will make Earth uninhabitable, not out of malice, not as punishment, just as a consequence of physics. And the clock isn't loud. It doesn't tick. It doesn't warn us. It just burns. And this is the part that should make you uneasy, because this one doesn't wait for the distant future. This one could happen tomorrow. Let's rewind to September 1st, 1859. On that morning, an astronomer in England named Richard Carrington was doing something ordinary. He was observing dark blemishes on the sun, sunspots, when something extraordinary happened. Right in front of his eyes, two brilliant points of light suddenly erupted from the sun's surface. They burned intensely for several minutes, brighter than anything he had ever seen. Carrington had no idea what he'd just witnessed, but history would later recognize it as the most powerful solar eruption ever recorded. Less than a day later, about 17 hours, the consequences arrived at Earth. The planet's magnetic field was slammed by a flood of charged particles, so intense it overwhelmed 19th century technology. Telegraph wires sparked. Equipment ignited. Operators were shocked by currents running through machines that weren't even plugged in anymore. Messages were sent using energy pulled directly from the storm itself. And the night sky turned blood red and green. Auroras spilled across the globe. People as far south as the Caribbean believed dawn had come in the middle of the night. This event became known as the Carrington Storm. Now here's the uncomfortable truth. If that same storm hit Earth today, it wouldn't be a historical curiosity. It would be a global catastrophe. A storm of that magnitude would induce enormous electrical currents in power grids around the world. High-voltage transformers, the backbone of modern electricity, would fail catastrophically. These aren't devices you replace in a weekend. They take years to manufacture, and there is no global reserve waiting in storage. When the grid goes down, everything goes with it. No clean water, no fuel distribution, no hospitals operating at scale, no refrigeration, no internet, no banking systems, no communication. Civilization doesn't collapse because of fire and explosions. It collapses because systems stop talking to each other. And experts estimate that a direct hit from a Carrington-level solar storm could leave major regions of the world without power for months or even years. Not days, years. During that time, supply chains would fail. Food wouldn't reach cities. Medicine would become scarce. Social order would fracture under the pressure. The loss of life wouldn't come from the storm itself, but from everything that follows. Tens of millions, possibly more. And here's the part that should actually scare you. This already almost happened. In July of 2012, the sun unleashed another massive eruption, one comparable in strength to the Carrington event. We know this because modern satellites measured it directly. Earth missed it by about a week. If the sun had rotated slightly faster, if the eruption had occurred just days earlier, modern civilization would have been blindsided. Researchers estimate the odds of a Carrington-scale storm striking Earth at roughly 12% per decade. That's not a cosmic fluke. That's a recurring risk we're choosing to live with. Now connect the dots. There's a slow threat, the sun gradually brightening until Earth can no longer support complex life. There's a middle threat, climate instability and biological collapse long before the oceans boil. And then there's a fast threat, solar storms capable of dismantling civilization in a single day. So what's our plan? We don't have one. We have no off-world populations, no self-sustaining colonies, no realistic evacuation path for our species. We've explored space, yes, but cautiously. Symbolically, we visited the moon and left. We've built a station that depends entirely on Earth for survival. If disaster struck tomorrow, we'd have maybe 15 hours of warning. 15 hours to protect a planet-wide electrical system that has never been shut down all at once. And beyond that, the larger timeline looms. Because the sun isn't unique. It isn't malicious. It's just doing what stars do. Every star brightens. Every star changes. Every star eventually renders its inner worlds uninhabitable. The universe isn't hostile to life. It's indifferent. We evolved under the star. We built societies around its energy. And none of that changes the physics governing its future. We are temporary occupants on a planet with an expiration date. So remember these three things. First, the sun is not static. It is changing, heating, intensifying, and it always has been. Second, solar storms are not science fiction. They are real, recurring threats we are dangerously unprepared for. And third, becoming a multi-planet species is an ambition. It's insurance. Every day we remain confined to one world. We're betting everything on continued luck. Tomorrow morning, when sunlight hits your face, remember where it came from. 8 minutes of travel, 93 million miles, from a nuclear furnace powerful enough to sustain life, and eventually end it. The sun gave us time. What we do with it is the only thing that matters. I'll be watching the sky, and maybe you should too. To understand why solar storms pose such a serious risk, we need to look at the physics behind them. The sun is not a solid object. It is a plasma, a gas so hot that electrons are stripped from atomic nuclei. This plasma is in constant motion, driven by heat flowing outward from the core. Because different parts of the sun rotate at different speeds, its magnetic field becomes twisted, stretched, and tangled over time. These magnetic fields store enormous amount of energy. When they suddenly reorganize or reconnect, that stored energy is released in an explosive event known as a solar flare. Often, this is accompanied by a coronal mass ejection, or CME, in which billions of tons of magnetized plasma are launched into space. A CME is not just a cloud of particles. It carries its own magnetic field. When that field interacts with Earth's magnetic field, the orientation matters. If the magnetic fields are aligned in an opposing direction, energy transfer becomes extremely efficient, allowing charged particles to penetrate deep into Earth's magnetosphere. This interaction induces electrical currents in long conductive structures on Earth's surface. Power lines, pipelines, undersea cables, and railway systems can all act as unintended antennas. The longer the conductor, the stronger the induced current. This is why modern electrical grids are particularly vulnerable. They span thousands of kilometers. High-voltage transformers are especially at risk. They are designed to operate with alternating current at precise frequencies. Geomagnetically induced currents introduce direct current components that cause transformers to overheat, saturate, and permanently fail. Once damaged, these transformers cannot simply be repaired on site. They must be replaced entirely. From a systems perspective, the danger is not the initial failure, but the cascade. Electrical grids are tightly interconnected to balance load and maintain stability. When one region fails, the strain shifts to others. This can trigger widespread, self-reinforcing blackouts. Similar cascading failures have been observed in much smaller events, such as regional grid outages and ice storm failures. Satellites face a different set of risks. High-energy particles can damage onboard electronics, degrade solar panels, and disrupt orientation systems. Atmospheric heating during strong solar storms increases drag on low Earth orbit satellites, causing their orbits to decay. During past storms, dozens of satellites have experienced anomalies or been lost entirely. Earth's atmosphere provides significant protection for life at the surface, but it is not static. Over geological timescales, solar radiation slowly strips lighter molecules away. Mars lost much of its atmosphere after its magnetic field weakened. Earth's magnetic field is stronger, but not permanent. It has reversed many times in the past and can weaken during transitions, increasing vulnerability. From an evolutionary standpoint, life on Earth exists within a narrow window of stellar stability. That window is defined not just by temperature, but by radiation levels, atmospheric retention, and magnetic shielding. As the sun evolves, each of these factors shifts. For students of science, the key lesson is that habitability is dynamic. It is not a permanent property of a planet, but a temporary balance between stellar output, planetary geology, and atmospheric chemistry. The challenge humanity faces is not stopping stellar evolution. That is impossible, but understanding it well enough to adapt. Whether that adaptation takes the form of hardened infrastructure, early warning systems, off-world habitats, or entirely new technologies is still an open question. What is clear is this: the sun is not just a source of life on Earth. It is also the ultimate boundary condition for our future.